The industry is shifting into autopilot territory. AI is moving from tools designed to answer questions to agents designed to deliver autonomous outcomes. The standard approach to building these agents is simple. Hand a large language model a massive list of API tools and tell it to figure out the rest. Giving an LLM unconstrained access to your system introduces unbounded execution risk. The agent's path to a goal is entirely unpredictable. As complexity scales, the agent's internal logic separates from the actual database. The AI makes decisions based on a reality that no longer exists, a condition known as silent context drift. True, safe autonomy at scale cannot rely on open-ended tool lists. It requires a constitutional architecture. This diagram outlines the constitutional operating system framework, which is divided into 4 distinct layers. At the top is the law layer. These are the canonical rules that definitively dictate correct system behavior. Beneath that are the process and execution layers, where the actual bounded automation occurs. Finally, the enforcement layer runs automated validation checks to prevent the system from drifting away from the law. Scalable, safe AI autonomy is achieved by engineering uncompromising constitutional constraints, rather than granting the system maximum freedom. We start by defining the strict baseline boundaries of the user interface. The architecture is governed by the 12-9-6-3 bound, maximum 12 apps per hub, 9 sub-navigation items, 6 quick actions, and exactly 3 AI verbs. Those 3 reactive verbs define the baseline AI constraint. They are explain, route, and unlock. Explain is a low-risk capability designed to provide information and clarify context for the user. Route is another low-risk capability that safely navigates the user to a specific destination within the platform. Unlock operates at a medium-risk level, surfacing gated paths or premium upgrades. This diagram illustrates the defining constraint shared by all 3 verbs. They must be strictly initiated by a user action. The system only reacts. By limiting the AI to these user-triggered responses, the system's execution risk remains structurally low. But an autopilot system requires the AI to initiate contact, to surface insights, or run workflows unprompted. The current rules explicitly forbid this. We cannot build proactive intelligence on a reactive verb model without breaking the established constitutional law of the system. This contradiction is the governance gap. To bridge this gap, we engineered a 4th verb that operates completely outside the reactive boundaries, the act verb. This split flow compares the 2 architectures. The new act verb moves the trigger away from a user action, tying it instead to a system condition. These permitted triggers are strictly defined. They rely on scheduled cron jobs, edge function metrics, or real-time event subscriptions. However, granting a raw, untyped act command to an AI agent is too broad and dangerous for production environments. To control execution, we use strict subtyping to map autonomous actions directly to a severity hierarchy called the intervention ladder. The first subtype is act:"notify. Operating at level 0 severity, it is restricted entirely to low-risk information push operations. The second is act:"execute, mapped to level 1 and 2 severity. This allows the AI to run bounded, pre-approved workflows on the user's behalf. Because act:"execute alters data, it carries a mandatory engineering requirement. The system must possess strict rollback capabilities to entirely reverse the action. The final subtype is act:"escalate, at level 3 severity. This is never fully automated. It is used strictly to alert a human operator. Subtyping acts as a structural safety net. It takes a broad do-anything command and forces it through a deterministic, risk-gated pipeline. System-initiated actions cannot exist in a vacuum. They require native architectural state management to remain deterministic. This schema is the context envelope. It carries the exact state of the user and the hub, expanding to reveal new top-level fields. First, act:config explicitly defines platform-level availability. Second, pending acts queues unexecuted system actions waiting for approval. To process the items inside that pending queue, we employ a 2-tier consent model. The first tier is called notification consent. This serves as a single, persistent opt-in that allows all act:"notify" operations to run. The second tier is called action consent. This requires explicit per-workflow approval from the user before any execute or escalate operation can begin. The system enforces an immutable rule. The AI must secure consent before execution starts. It cannot execute an action and request consent retroactively. Unconsented actions are governed by a 48-hour time-to-live deadline. Once the timer expires, the pending act is automatically canceled and logged as denied. By embedding consent directly into the envelope data model, the AI is physically incapable of executing an operation without verifiable database approval. Even with strict verbs and state envelopes, agentic systems face governance drift as they scale. Silent drift occurs when the agent's internal skill context separates from the actual database schema over time. The AI begins operating on stale instructions. We eliminate competing sources of truth by deploying the authoritative source sync pattern. This visual shows the sync query in action. It detects discrepancies between the primary database table and the agent's local context file. The sync automatically overwrites the AI's context with the primary database truth, requiring no manual judgment. Deterministic verbs and perfectly synced state enable complex multi-agent orchestration. Parallel worker agents execute independent tasks simultaneously, relying on that clean context to prevent errors. All parallel workers must eventually combine their outputs at a choke point called the merge gate, where they wait for authorization. Following the gate, a dedicated compliance agent sweeps the unified state, ensuring zero drift before the final system acknowledgement is issued. True, scalable AI orchestration in autopilot territory is only possible when autonomy is engineered on uncompromising constitutional constraints.